everybody. I am now recording. Hopefully, let's see, make sure everything is good. Okay, well, we'll see. Okay, well, thanks everybody for calling in, and glad that everybody didn't have too much of a problem. There's always a bit of a problem with these kinds of things. So to begin with, and don't feel guilty if you weren't able to do this, but I need to know if you were able to go through and read the things that I'd asked you to read. So, and if you have, I want to see if there are any questions on the reading, both the previous year's poster and proposal, the proposal that I wrote, just to get a good sense that if everybody is okay with the target of our project. I'll just do a quick roll call. Gary, were you okay with everything on the reading? Were you able to get around to it?
Yep.
How about you, Jamie?
Yep, I was able to get on it. I read it, and I watched Luisa's video. I'm going to have to watch that another 2 or 3 times probably to get some of the stuff in there, but...
Okay, that's good. Yeah, that was going to be my next question, but let me just finish off with the reading. Laura, were you able to get around to doing the reading?
Yes, I did the reading, and I think I'm starting to understand the AGN a bit more.
Okay, and Howard?
Yes, I did.
Okay, and the video was, I think, longer. That's a bigger, yeah. So everybody get a chance. Jamie said she watched the video. I'm assuming Laura has, since she was working with Luisa previously. So Gary, did you get a chance to watch the video? Gary, did you get a chance to watch the video?
Yes, I did.
And how about you, Howard? Okay, great. So is there any sort of burning question anybody wants to jump in with in terms of any of the things that were there, just the purpose of the project, the whole idea of just general infrared access, or the specifics of looking things up at, in the catalog? I'm sorry, you broke up there a little bit. What was that again?
Why was the proposal rejected?
Oh, yeah, somehow the volume on your side has gotten very low, Gary. But yeah, if the proposal was rejected for, I can't remember even the specifics. You usually get a little response as to what it was, but I think part of it is, and I'll do sort of a general statement, is that it's too much of a fishing expedition. And the trend is not towards fishing expeditions these days in terms of which proposals are awarded. Now, I completely comp to that. That's not untrue. That is exactly what it is.
There's so much data that hasn't been looked at.
Right, that's the thing. What they want is a much more clear through line between, what the data that hasn't been looked at, what you're going to do, and what the final science is, basically sort of what's the first, paragraph, or what's the abstract of the paper that you're going to be publishing in many ways, which is, again, in general, not an unreasonable demand, because oftentimes proposals are very scattered, unfocused, and so on. And I think that even when I'm reviewing proposals, I want somebody to make sure to tell me exactly what they're doing or what their final intent is. The difficulty here is that this is but there are these large data sets that you want to be able to look through. And you usually do this in terms of surveys. That's what you do. You do a large survey to try and pick out something, and that's what I presented our proposal as, that this is effectively a very large survey. Of course, as a survey, it has many things lacking, that as surveys have a very specific design, how deep they're going, which means the exposure time, wherever you're surveying, is more or less essentially the same. the various conditions are all the same, but of course our bits and pieces, when everybody was pointing Spitzer at different pieces of the sky, nobody was doing it identically. So there's definitely issues there that we will have to deal with, because this is not like any other survey that's ever been done. But it's sort of, it's too much of, it's just winds up being in these cracks, in my view. Again, I don't radically disagree with the assessments that I've gotten on the proposal. I don't think, it's not like they didn't get it, but it is one of these strange areas where you're not being specific enough, which we're not. But if it's if you're analyzing a survey, well, what's the parameters of the survey? At the end, what can you say? When you've discovered these kinds of things, okay, we have gone through such and such a depth and discovered all the sources or some percentage of the sources, because we know what the survey parameters were. But the survey parameters here are incredibly diverse. But why do it is just that, it's one of these things that these unusual sources could be are lurking there with nobody having ever seen them. And so whenever this kind of a proposal comes up against something that I will look at this database for this object in this survey, or very specifically, I think these kinds of fishing expeditions tend to lose out, because then they know exactly what they're getting. They know what the result is going to be. I am going to discover, X number of this kind of AGN. I'm going to discover this kind of young stars, and anywhere between 200 and 300. So they don't need to be specific, but they're more, they're promising something that's a little bit more concrete. And so I want everybody to be aware of that. That this is, I'm not trying to hide that fact. This does not go in that direction. On the other hand, I think if you don't look at the data that's just sitting there, then you're just wasting it. All this data has been taken, it's been reduced, the catalogs have been made from them, and nobody's looking at it. So from that standpoint, in my view, it's a tragedy and a travesty. On the other hand, from whenever you're in a position of looking at multiple proposals to do things through the archives, things are just simpler when you say, oh yes, give it the time, give the money to this person to look for this specific thing in this specific catalog. It's just simpler because it's simpler to understand, and you know what you're paying for, essentially, that there's some statistical likelihood that they'll get X number of this kind of object. There's no way we can promise that. Any other questions?
When I was looking at the proposal, it said I think it was above 5 micrometers that we'd be looking at. Was that I don't know if the units are right. I can't remember the units right away. But I know, when we were talking in person, were we going to look at something smaller than that as well, or was 5 going to be like the limit, or?
It really depends on how quickly we're progressing. I think the big advantages of this catalog are that the WISE survey, remember, we're trying to be unwise, but the WISE survey has done 3.5 and 4.5 microns, and then it does 12 and 22. Spitzer did 3.5, 4.5, 5.8, 8, and 24. So the 5.8 and 8 aren't really matching up with WISE, but in terms of sensitivity and, of course, sky coverage, which WISE covered most of the sky, in fact, almost all the sky, they would have probably picked up the 3.5 and the 4.5, even though we're not at 4.5 excess, we're at 3.5 excess. We're still, Spitzer in many ways is more sensitive than WISE in those areas, but I think a real bang for our buck in terms of things that have not been looked at is going to be at 24 microns, because Spitzer is way more sensitive than WISE is at 24 microns. And in fact, the way the images were taken for the 24 microns, and I was looking at AGN, and I proposed several AGN to look at, it couldn't do a small piece of sky. It just inherently wound up doing a giant piece of sky around your target, for a whole host of reasons, which we can get into if you want. But the reality is that, so the 24 micron, every time it was a targeted exposure, would end up giving you a lot more sources around your source than you ever were interested in. And that was the case with me. And I know there are all these AGN that I imaged, and I had all these sources around them that I really didn't care about. And most of the sources tend to be either foreground stars or background or similar galaxies. So I think that's where we're going to get the bang for our buck. So I think our first order would be to look for 24 micron excess being our primary target to figure out which sources show 24 micron excess. That comes from warm dust. It doesn't come, I mean, if there's a 3.5 micron excess or a 4.5 micron excess, or particularly, if we're just looking at the Spitzer data, we need something that sort of does that notch or starts bringing things up. So if we take the 3.5 as being the stellar light or star light from all the stars, or just one star's stellar light, so we would be looking at 4.5, 5.8, and 8 micron as excesses. But 4.5 micron light is very short wavelength, which means it comes from the peak of the peak of the black body is shifted towards much shorter wavelengths, around 4.5 or 5 microns. That's really, really hot dust. 24 micron, it's coming from much cooler, though still fairly warm dust. So that's, I think it's a worthwhile place to look. And again, hopefully, certainly come up with sources that others have not found just yet. So that'll be our first step. Now, if we sort of breeze through that, which is, I would say, rather unlikely, but possible, this is not a reflection on your capabilities. That's just fundamentally, these things just take a long time. So if we do that, then we can say, certainly when we look at 24 micron excesses, one of the things, if you remember from the proposals, is if there's a 24 micron excess, then we really want to go back and see if that excess is starting to pick up around 8 and 5.8 and so on. So it doesn't matter if they're not there, that's okay. But that certainly verifies it in some ways. But if we do that, if we pick out all the 24 micron excesses and we're happy with those, then we might switch over to pick shorter wavelengths as our excesses. But I think first we're going to target 24 microns. A very long answer to your very well placed but shorter question.
No, that's fine. I think what it was is I had forgotten that Wise did the 3.5 and the 4.5, and that's what had me a little bit confused. That's all.
Okay, no, not a problem. We're going to have to repeat all these things because I forget them too. So it's, oh, right, that's why we're doing that. Any other questions? Anything having to do with, the design of our survey, or how we're going about trying to pick out these sources, why we're doing it, or any of the things about the infrared excess? Just again, these are general questions. I'm going to put out more specific things for everybody to do before we start writing the proposal.
I have a question on the signal-to-noise ratio.
Yes.
So that, from the images you have, is how sure you are that those points are clear points without any extra contamination, right?
Essentially, yes. The SEIP was trying to be as general as possible, so they had to make a compromise between picking out as many sources as possible, because Spitzer obviously detected a lot of sources, but also making sure that those sources were reliable. So, but I think their catalog has everything that's 3 sigma, or signal to noise of 3 times the background, and above. I am less, but I don't want us just to go by what they have said, because in particular, they were just doing it, for each of the different bands. What I want us to do is to go through and pick high signal to noise for the channels that we're interested in, certainly starting about 24 microns, and then start walking it back in terms of signal to noise. And then for us to come up with what we consider not only just, because remember, each of these channels was done independently. They have not what's called been band merged. So each one is sort of more or less saying, okay, there's a source at this right ascension and declination, and then it says, oh, is there another source that's within 1 or 2 or 3 arc seconds of this source? And it says, okay, yes, there is one, and I'm going to associate my 24 micron source here with that 8 micron source there. But in reality, they never went and checked by eye, or had a separate program to make sure that those were just really coincident that they're the same source. So first I want us to pick, sources, a signal to noise that says, okay, yeah, I look at that on the image and I'm convinced that there's a source there. But then similarly, we have to contend with the other wavelengths and the other channels because we have to create an SED. We can't create an SED just with one point, so we need to have the other points be pretty well defined as well. So then we can reduce their signal to noise to the point where we still think, this is a viable source, and then those, whatever the lowest is, whether, I mean, the original one we set at 10 sigma. 10 sigma is really conservative and safe, but but it didn't give us that many sources. But it did say that there were sources there, and that's why I did SIRXS. That was the result, I think, of the first round. For us to go deeper, hence our name, we're going to have to dynamically walk it back in signal to noise and see where we're comfortable with A, the sources being real, and B, that source having enough signal to noise in all the bands, or at least several of the bands that we're interested in, and certainly the 24 micron, to be sure that we can make an SCD and say, aha, yes, I am confident that these are real detections. There's a real uptick based on at the 24 microns, but of course at the end we also have to go back and look so that they're not confused sources. That is, they're not coincidentally nearby and we're thinking there's an infrared excess, but we have to actually visually check them, which means.
So are we gonna check them via finder chart or via the night or something?
Yeah, we're gonna use finder chart for that. And that's I think one of the places where we're going to be able to distribute the tasks amongst the various groups, depending on how many students we have. But that's also because we have to do this by eye at some point. Dropping the signal to noise too much, if it gives us a million sources at the end, is not worthwhile. So we're going to have to be. Sorry.
I think I'm good to about 500.
Yeah, I think that's about right-ish, anywhere between 500 and 1,000, and, we can try and automate some of the bits, but at some point we have to, have eyes looking at them, and that means that there's a limit to how low we can go on our signal to noise.
Right.
Any other questions or comments?
You went with this. I believe I'm right that the conclusions were whether they were extragalactic or galactic. Have those sources been identified with any more precision? Or looking for dusty galaxies, or we're just going to look and see what we can find?
We're going to look and see what we can find, but we have a bit of a broadsword in this case to sort of split our targets, but we don't have a scalpel. So yeah, in a broad way, we're going to be able to say that the sources that are fainter are likely to be extragalactic. The sources that are brighter are likely to be galactic. And also, when we're looking at the sources, obviously, if it's a fuzzy extended source, which is that's going to indicate that it's most likely a dusty galaxy of some sort. Once we have identified them, and we've sort of put them in these two bins of nearby, far away, then I think we can decide about which ones we're going to pursue about, to more specific identification. And that the more specific identification can be, basically we'll have two aspects of it. One is literature searches, or just looking up things on the web, where either in a NASA extragalactic database or there's this other database called SIMBAD, which is about all stars. That is, has this source been cataloged in some fashion by somebody else? If it has, did they say anything about it? Did they say, yes, this is a young star with an infrared excess, or this is an evolved star with dust coming off of it, hence that's where its infrared excess is coming from. Or if it's an extragalactic object, this is an ultraluminous infrared galaxy. We want to see, we're obviously going to pick up things that other people have picked up before, so we want to make sure that we're not, quote unquote, discovering something that it's already been known. So that's the first step to do this. So once we've culled through the ones that have previously been identified, then that leaves a sample which then needs to be spectroscopically identified. For that, I have to take that sample and then propose it to a ground-based telescope for me to take a spectrum, and then we can start deciding, oh, these were all, all AGN or star-forming galaxies or luminous infrared galaxies, or, for the faint sources and for the brighter ones, oh, look, this is a carbon star because it's an evolved star. This is a young star. Wow, it's unusual. That young star shouldn't be, it should be in a young star forming region, but it doesn't seem like it's very close to it, or something like that. But that's sort of the step that will come after NITAR. We need to identify the sources that are interesting, B, group them into the near and far, and between those, once we know they're near and far, look in the near catalogs of star catalogs. Has anybody seen something, these guys before? Similarly, for the extragalactic catalogs, go back and look there and say, hey, did anybody notice this guy before? Everybody okay with that? Following the sort of logic on this?
Yeah. I'm actually happy that it doesn't seem to be too far off of what I already know kind of how to do.
Yeah, this is actually, of my projects that I've done, this is the one that's closest to the one that Luisa has done in her projects. This one doesn't uniquely, concentrate on AGN. It just concentrates on anything that has an infrared excess, which happens to be both AGN and young stars, and carbon stars, and oxygen-rich stars, and various other varieties. But at the end, like I said, I think the worthwhile aspect of this that I'm hoping to get is really find unusual sources that have, short lifetimes, that we generally don't get picked up unless you do a very large survey. And hey, guess what? Even though this was not just one giant swath of the sky or even the entire sky, we have a very deep survey going here, and so that's worthwhile to look into. It just happened to be made up of a lot of pinpricks. Okay, any other questions?
When I was looking at Luisa's video, and she was talking about SEDs versus black bodies, and how they're not the same. So are we going to be looking at the SEDs? Is that what we look at, and then compare them to black bodies?
Yes, essentially yes. Although we don't, ideally, if you saw it in my proposal, I have a collaborator who has a program that fits SEDs fits black bodies to the SEDs that we get. So the SED is the telltale sign that there's something there that is giving us excess energy in the infrared. What temperature it is, we have to back out of that sort of, and the way you back it is you fit a black body or multiple black bodies. See, there's a hot one and there's a cool one, and this cool one peaks at this wavelength, which means that that's coming at, on average, the majority of the sources are 300 degrees Kelvin or something like that. So yeah, that's the critical thing to remember, is the data that we get is the SED. That is, samples of the combined black body of your main source and its infrared excess.
And then it's when you determine how much excess it has and everything by comparing it to one or more black bodies to see the temperature comparisons again.
Right. Well, the critical thing is what you want. For example, if it's a star, if you're getting most of your dust is emitting anywhere between 300, or 300 Kelvin, 200 Kelvin, that's basically telling you that it's an asteroid belt around that star, because that, or nearby rocks that are fairly warm. If it's giving you 50 to 100 Kelvin once you do your infrared excess and the black bodies, and again, we're at 24 microns, we're more sensitive to the asteroid belts than the Kuiper belts, but then that's telling you if it's cold enough, you fit a SED, and then you fit black bodies to your SED, and you're like, oh wow, look, you're peaking at around 70, 80 Kelvin or 100 Kelvin. That's not a nearby asteroid belt. That's much more likely if either near very far away Kuiper belt like we have around our sun, or it's a very dim star with an asteroid belt, but it's dim. It's not heating up its asteroids as much as our sun is heating up its asteroid. So there are various different permutations of this, but it does tell you what you're looking at, and again, that's in the context of stars and their infrared excess. In terms of galaxies, once you do the fitting, more often than not, if it's very cool, what ends up happening is that means there's a lot of embedded star formation. So a lot of that energy isn't actually still getting out at the 24 micron level and so on. But still, it's telling you, if it's very embedded, that means there's a lot of dust and gas in that galaxy. So there's clearly, this is a potentially, eventually will become a very luminous galaxy. But yeah, it's the SED is what we detect. The black body fits tell us temperatures, and then we have to apply just the basic physics of how could you get this excess at this temperature based on extra information. How hot is the star, or how, what's going on in that galaxy. Like I said, if it's a very hot star and you're getting very hot dust emitting, well, that still could be, the dust could be very far away from the star because the star is so hot, it's still warming it up very far away. If it's a cool star and you're getting a lot of hot stuff, then that means the dust is really close by. So these kind of logical conclusions based on that. So, but fundamentally, first we identify the infrared excess, and then, once we have those sources and sort of categorize them into these two different categories of nearby and far, then one of the things that we can do with them is do the black body fitting to get more information. That's, again, outside of the scope of what we're going to be doing, but that is the ultimate goal of what we need to sort of to think about. Okay, any other questions?
What is a QSO?
QSO is one of the very many names that were given to active galactic nuclei before everybody knew what they were. So the first ones that were detected were these QSRS, quasi-stellar radio sources. And then a whole group of separate of them that didn't have any radio emission were detected, and they were labeled quasi-stellar objects. And then there were these other category of very luminous nearby nearby galaxies that weren't that luminous, but certainly had excess energy from their centers. These were the Seyfert galaxies. It's all giant black holes at the centers of galaxies accreting. It just took people a long time to know that the taxonomy that they had come up with, all of these different sources, in fact, were the same thing. But the names have remained. So QSO, QSRS, Seyferts, all of these exist as various the trunk and the tail and the legs of the elephant, with everybody just sort of going around. If you know that classic thing, blind men sort of feeling an elephant. One says it's a snake, one says it's a rope, one says it's a tree trunk, but it's all the same.
Yes.
It's an elephant.
Okay. I think that was the only part of the proposal that I wasn't quite sure of and I hadn't looked up.
Okay, we're coming up to the end of about an hour, so I'm usually don't want to push it too far, although I will certainly go beyond if we need to, but let me do a quick roll call to be sure everybody's okay. And I'll give you more stuff to look at and instructions to do new things in terms of we're going to be using TopCat and so on to start getting used to that, but then also start thinking about how we're going to be writing the proposal. Just a reminder that everybody's going to write the proposal separately. I want everybody to individually write the proposal, and then we'll merge them all together and do the best of from all of them. But fundamentally, I want you to think about how you write the proposal, so that gets you thinking and used to what we're doing in terms of not just understanding what we're doing, but in being able to articulate it. And so in this case, I think writing on paper always forces me certainly to come up with a better understanding of what I'm doing. So this is all sort of working towards that, but I also want us to start getting the tools in hand that we're going to be using. And so, but let me just before that do a quick roll call and see if everybody has any last questions. So Gary, any questions?
Nope, I'm good.
Jamie, how about you?
No, I think I'm good now.
Okay, how about you, Howard?
One quick question. We're calling the different wavelengths If I got what I need to get a lot of the I'm sorry, the YouTube presentation, Luisa's YouTube,
Mhm.
those are filters, and they're just filtering through a certain wavelength, and we're looking at different wavelengths that have been filtered. Is that correct?
That's exactly it. So when I'm talking about 3.5 microns or 24 microns, it's the same as saying I'm looking at, red light in the optical. That is, you put the filter in front of your camera, and you're only letting either red, blue, green, whatever those wavelengths are through to your detector. Of course, we sort of lose, the language becomes inadequate, obviously, when you're entirely in the infrared, so we just use the central wavelength of those filters. If you remember, she had little filter graphs, but the main thing being that, yes, if I say 3.5 microns, it's a little narrow area between like 3.3, I think 3.9 microns that is being let through for the detector to detect.
And so we're looking at like the characteristics of the sources at each filtered wavelength, and then also the differences on the color diagram.
Exactly. That's the critical part, is that, remember that because magnitudes are in logs, what we're looking at is not really the difference, but the ratio. And so in the color diagrams, we're looking to see if the ratio is the ratio of a black body. So if the ratios of a black body, when you take the ratio / difference, it should be 0. That is, if it's exactly the same as a black body, then there should be no difference. That is, each of those points is populating the part of the black body spectrum at that wavelength at exactly the same ratio between, for example, 3.5 and 4.5 microns. And of course, when we get the infrared excess, is that ratio is telling us that, wait a minute, 24 microns should be way lower for a black body here at this temperature. But now we're way above here, so that's really giving us a clue that we have diverted from the classic black body, and there's excess energy coming from there, and that's why the color diagrams are useful, is that it's very easy to see whenever you're not at 0, that anything that's diverting from 0 is telling you that this is not black body-like. At those wavelengths, at those filters, whatever, that we're looking at. So just as another example, your source could be entirely black body, like between 3.5 and 4.5 microns, between 4.5 and 8 microns, but then you get an infrared excess at 24 microns, so you really are only getting the color shift, or the difference between 24 and 8 microns is off of the black body curve, but the 3.5 to 4.5, or 4.5 to 5, and 5 to 8 all could still be black body-like, and so that's fine. So that's the critical thing, is when we're going to be looking at, at which ratio of filters between one and another are we diverting away from a black body. Yes?
So when you say 0, you don't really mean 0, right? Because the flux at 3.5 and 4.5, say for instance, would be very similar to each other. And so when you take the ratio, you're going to get close to 1, but you're never going to get 1.
No, you're close to it. This is the thing that always gets confusing, is that what you're doing is you're not comparing the flux at 3.5 microns and the flux at 4.5 microns. You're comparing the flux compared to a canonical black body at 3.5 microns. And you're comparing the flux that you're getting to what you would get to a black body at 4.5 microns. And therefore it will in fact be 0 if the ratio between those two, it'll be exactly 0 if it's exactly on a black body. So that's a real subtlety which we'll come back to again and again and again. But it's a non-trivial one, because the magnitude system is not a simple measurement of how much light you're getting. It's how much light you're getting at that wavelength compared to a 10,000 degree black body. So that you could get 0 if you're in fact looking at exactly something behaving like a 10,000 degree black body, or basically like the Rayleigh-Jean side is basically the same. So the slopes, it's the ratio between the two, but the ratio compared to a black body. But you're absolutely right. The fluxes are never going to be the same. I mean, that's the definition of it. There's no way something is going to have a flat flux, across multiple wavelengths.
But you're not comparing fluxes against each other. You're comparing fluxes against the ideal black body.
Exactly.
Okay. All right.
And that's why color diagrams work, because you have sort of reset your measurement. You make a measurement from the sky of light coming from an object, but then you put it in this context of comparing it to a 10,000 degree black body. Once you've done that, that's why when you do the difference between magnitudes, or which is of course the ratio between those two, that really quickly says, oh, if it's like a black body and you take the difference, you're gonna get 0 or very close to 0. And that's why we do it. It's not a trivial concept as to why it's done like this, but once you see how you're doing it, how the results of doing it, you can see why it's so worthwhile. In terms of explaining it, it's not so easy. It took me a long time for myself to absorb all of this into my brain, to have it be intuitive that, oh, okay, this is, I'm taking what's the magnitude between this, magnitude between that, take the difference, so this is the number. So, it's like a black body, or it's off of a black body, or it's too blue, too red, and so on. But I would definitely recommend, if you have the chance, to look through Luisa's video again. It's this very strange concept of the magnitude system, that it's not purely a measurement of flux. It's a flux as a ratio to an ideal black body.
The fact that it says 3.5 minus 4.5, it makes it seem like comparing the fluxes, the ratio of the fluxes from that source.
Yep, you're absolutely correct. That is, if you're coming in cold on this, that's exactly what it is. The fact that there's brackets around it, to an astronomer, which you have to start paying attention to that. If it's bracket, it's telling you it's a magnitude, therefore it's already taking in with respect to a 10,000 degree black body. And what bothers me often with some astronomers is they become so used to this that they start leaving off the things that are supposed to be there, like brackets, or mentioning that it's a magnitude, and that can leave things to be very confusing. So
yeah, that's what she was saying about how it's all referenced to Vega.
Yep. And it's not even Vega itself, because Vega itself has an infrared excess. So in the infrared, it's not even close to being an ideal black body. So what we've now done is switched away from Vega to an idealized, perfect 10,000 degree black body, which Vega is mostly in the optical and the UV, but boy, is it not an idealized black body in the infrared. But nobody knew that until this satellite called IRAS flew in the early 80s.
Yeah. Interesting. Okay.
Okay, any last questions before we sign off?
I don't think so.
Okay, well, thanks a lot, everybody, for calling in. I've recorded this, and I'll upload it I'll probably upload it tomorrow if anybody wants to go back to any of the parts, and then there'll be a couple more instructions, and we'll meet again next Tuesday. Thanks again, and hope...
To do anything between now and then?
I'll summarize it in the email. It's mostly it'll be, I think, try and get TopCat running and working on your own machines, and then maybe a few other instructions. But fundamentally, I think I'll switch over to making sure everybody has that working, because then you can play around with it as you're writing the proposal, even though that's not necessary. But if you want to, I want you to have that option. But then after that, we'll switch to really just mostly writing the proposal. Okay, well, thanks a lot, everybody. Have a good rest of the week, and we'll chat again in a week. So long.